Okay, welcome back. So, in the last video, I showed you the derivation of the average velocity or the average speed of a gas being equal to the square root of 3RT over the molecular weight of the gas itself. Now, what this basically tells you is that the speed of the gas depends on two specific parameters. It depends on the temperature and it depends on the molar weight of the gas. Specifically, if the gas has lower and lower molecular weight, because the molecular weight is in the denominator of this equation, that will make the speed of the gas higher. And this is ultimately a corollary of the law of conservation of momentum of physics. The fact that if you have a specific amount of energy allocated to you, that energy is going to be dissipated in the form of mass and speed. And if your mass goes down, then your speed has to go up. If your mass goes up, then your speed has to go down for you to have the same type of momentum. And what you can think of in terms of the graph right here is that if you have massive particles like the green one and the pink ones right here in the box, their speeds are going to be a lot lower, represented by the smaller vectors shown right here. But if you have lighter molecules, ones that have smaller molecular weights, their speeds are going to be a lot higher at the same temperature. Okay, and that's represented by the longer vectors arising from the gases. Now, speaking of temperature, if you do change temperature, you will affect the speed of the gas as well. So increasing the temperature will have the effect of increasing the speed because the temperature is in the numerator portion of the equation. Okay, so the speed will go up. And that will be the same thing as taking your gas sample, held in some type of container and basically heating it up. If you start heating it up using a hot plate, you can introduce enough heat to change the temperature, and that will, in essence, speed up all of the gases. Doesn't matter if they have higher or lower molecular weight, all of them will have increased velocities, increased speeds, all relative to their molecular weights, of course, right? So the higher molecular weight substances will still have lower speeds than the ones with lower molecular weight, but every single substance here will increase, as you can see, in speed as a result of increasing the temperature. Okay, that's what the speed of the gas equation tells us. Now, another way to look at this is to think of the amount of gases that can have a particular speed. You could actually set up a distribution of speeds for a gas. And in the graph that you see right here, what we're basically showing is amount of gas, and even though the units right here have some funky numbers, you could think of the entire curve, the entire bell curve right here representing 100% of the gas present in your flask. Whatever the amount is, whatever the gas is, doesn't really matter, but 100% of the gas could be present underneath this entire bell curve. Now, the interesting thing is that if you increase the temperature, and you can kind of see that here, you will go from 73 Kelvin to 173 to 273 to 373, the speed of the gases, the average speed, which is the top portion of the bell curve, keeps shifting to higher and higher speeds. But this is the thing. If you have a receptacle, a closed receptacle holding this gas, as you increase the temperature, you're going to increase the overall average speed of the gas. That cannot be denied. We already saw that based on the equation of velocity. But you still have the same amount of gas present in the receptacle. So what's going to have to happen is that if you are to spread this bell curve further to the right, you cannot contain the same height. Because if you were to do that, you will go from having 100% to now having 200, 300, 400%. And that doesn't make any sense anymore. So what that means for these curves is that, yes, you can move to the right, but as you do move to the right, the height of the curve is going to get lower and lower and lower. And not only that, the spread of the curve is going to become longer and longer and longer. You can actually spread very close to zero speed and very close to high speeds while still achieving that middle ground of average speed altogether. But the idea is that as you increase the temperature of the gas, all right, as you increase the temperature, right, so concentrating on temperature, as you increase it, you're going to increase the average speed, which is what we're seeing with the main average values, the highest point in all of these curves. Um, but you're going to be spreading the amount of speed possibilities. And the idea right here is that the value we're calculating with the equation is the average speed only. It's basically the value on the top portion of the curve and nothing more. You can still have a lot lower speeds and a lot higher speeds, but on average, this is where you're going to be landing at based on the temperature. Just remember that at higher temperatures, you have a lot more spread of what the speeds can be. And looking at the molecular weight, there's a similar trend. Um, as you increase the molecular weight, since the molecular weight is on the denominator of the equation, you have a similar approach. Increasing the molecular weight decreases the overall average speed. And because you can only have in this premise the same amount of gas present in the same receptacle, what that means for the curves is that you will also increase the height of the curve as you increase the molecular weight. And in the process, you will also decrease the speed, but the same premise is still applicable here. You can increase the speed of the gas by lowering the molar weight, but upon increasing the speed of the gas, the average speed of the gas, you have to spread the curve left and right and lower its amplitude. Okay, so that's the whole idea in terms of the overall process. And the curve itself is giving you all the different possibilities of what the speeds of any one given gas particle could be. But on average, you'll end up landing up on the very top of the curve itself. Okay, so that's what these formulas are telling you. So the amplitude is lower and the spread is higher anytime the speeds go up. This is true regardless of whether you're changing the temperature or the molar weight. Higher speeds will imply lower amplitudes and higher spread. Conversely, lower speeds will imply higher amplitude and lower spread. All right, so I'm going to show you I'm going to go into an example of speed involving calculations. But before we do that, we need to first address the fact that this equation has a number of constants and parameters within it. All right, so let's take a look. First things first, speed is always going to be in meters per second. Those are the SI units of speed. But what we have inside the square root are values of atmosphere liter per mole Kelvin, the units of the gas constant. We have Kelvin for temperature, and then for the molecular weight, we have grams per mole. So it doesn't take much than a second to realize that something is messed up here, right? Unit-wise, how is it possible that you're going to get meters per second out of the square root? First of all, you don't even have meters inside the square root by looking at all the units right here. And seconds, definitely you don't have seconds. And the reason why you don't is because you are using, in this format, the wrong version of the gas constant. Here is where I'm going to actually show you that the gas constant can actually be expressed in many different formats. What I'm going to do is get rid of the units of atmosphere liters and reintroduce them in a different way in which we get meters and seconds present. All right, so the moles and Kelvin, actually, they can cancel out. That's not a problem. The problem is the grams, the atmosphere, and the liters. So let me re-equate what the gas constant can be such that we end up with meters and seconds in them. So we have 0.08206 atmosphere liters divided by mole Kelvin. Now, the idea is this. First things first, atmosphere is a unit of pressure. And from the point of view of physics, pressure is better regarded in terms of pascals. And pascals have units of kilograms over meters second square. So if we divide by 1 atmosphere and multiply by the corresponding pressure in pascals, which is 101,325, we cancel out the atmospheres and now we introduce kilograms, meters, and second square. So that's kind of good because now we're going to introduce units that can give us ultimately meters per second for speed. By the same logic, looking at volume, well, the volume in liters is the same thing as 1,000 mLs. And for every 1 ml that you have 1 cubic centimeter, right? So now mLs cancel out. But if we're going to go with the physics definition, cubic centimeter is not good enough. We actually need to go all the way to cubic meters. All right, and that means that for every 100 centimeters, you have a meter, but this needs to be cubed. And that means that the 10 to the second will become 10 to the sixth. And that becomes the conversion factor for going from cubic centimeters to cubic meters. Now, the reason why I'm going through all this trouble is because we need to have meters and only meters for the units. And not only that, check this out, we're going to end up with kilograms as well. So when all is said and done, the meters here will cancel out with the cubic meters partially to give you square meters. And you're going to end up with the following units: kilograms times meter square over second square over mole Kelvin. But when you apply the entire multiplication of what's going on here, you're going to end up with a value of 8.3145 for the gas constant. Now notice the following. When you introduce the units, the new units of the gas constant, kilogram meter square over second square mole Kelvin, two things happen. First of all, the moles are going to cancel out. The Kelvin are going to cancel out. But now the molar weight is restricted to being in kilograms per mole. If you don't have the molar weight in kilograms per mole, the units will not cancel out. Okay? Alright, so let me show you an example to finish up the video. We want to determine the average speed of dinitrogen at 25 degrees Celsius. So that means that we need to use the speed formula. And what that means is that we have 3 multiplied by the gas constant in the form of 8.3145 kilogram meter square over second square mole Kelvin. The temperature needs to be converted to Kelvin, so 25 plus 273 gives you 298 Kelvin. And the molar weight of dinitrogen is 28 grams per mole. But you need to change that to kilograms. So this will not be 28 grams per mole, it will be 0.028 kilograms per mole. And now you will see that the kilograms cancel out, the moles cancel out, the Kelvin cancel out, and all that you have left over is meter square over second square, which upon taking the square root, voila, it's going to give you units of meters per second. Alright, so this is something very important to do, and I think at least at the very beginning, it'll be good for you to write down all the units so that you see that everything is canceling out. But with this, let's end the video right here.